when we did the inverted pendulum PD loop. So similar to that, we will apply techniques here. Okay, so so what a successive loop closure is, for example, if you remember the inverted pendulum case where I think it was two transfer functions, right? And one was f to theta, right? F to theta and theta to z. You remember that? So your position of the cart could be controlled using theta, and theta can be controlled using your force of the force that you apply on the cart, right? So the way you controlled was, okay, so you said, okay, you put a PD control here, assuming that whatever theta you are saying is available, that means the inner loop is much faster. So you design a PD for that, and then a different PD for this one. So two loops closed. So you always start with the inner loop, which is where the direct control. So inner loops are always faster because you want to separate. Like for example, if you want to change the heading of the UAV, you roll. So change in heading is much slower. If you want to change 90 degree, it will take a couple of seconds. And that should be slower. And it's on purpose. Otherwise, you can, your different control mechanisms. Because it's an under-actuated system, it's not like directly I'm controlling the heading. Right? You have to roll first and then your heading will change. So you purposefully make change in heading slower, and then you make this roll angle much faster. Similarly, the pitch will be much faster, but change in your height will be slower. So when you say go to that height, it will take a couple of seconds to it won't immediately reach to that height, but it can immediately change the theta angle to reach to that height, right? So so a successive loop closure is so basically in this plant what we are having here, the input to so your input is directly applied to y1. So that is like something like phi, and this is your aileron delta E, and then the output of the first loop is the input to the second loop, right? For example, here the output of the first loop is theta, which is input to the second loop, second transfer function, which is z. So that's how this is a cascaded system. Your the overall transfer function will be multiplication, right? What will be a transfer function from u to y3? If I'm saying u to y3, what will be the transfer function? A multiplication of p1, p2, p3, right? So all three transfer function multiplied will give you that transfer function. Okay. So the idea is you first close the inner loop, which is the most fastest. This is the fastest, and then this one, and then this one. So you're closing like generally we will only deal with two loops, but it's a general approach. But you have to separate them. This has to be faster. This is slower than this. This is slower than this. So you have to separate their speed. We can control that using omega n, if you remember from the previous case. Okay, so that's the whole approach, and we will apply this to all our states. And again, the idea is at frequencies below the bandwidth, that particular block can be considered directly. Like for example, if the DC gain is 1, that means I'm immediately getting phi. If you demand for a phi based on the speed of the outer loop, it is just immediate. So that means you can, when you're designing the gains or when you're obtaining the gains of the outer loop, you can consider the inner loop DC gain equals to 1 or k theta or whatever that DC gain is. That means at that frequency, it is just a steady state value. And what is the steady state value? It can be equal to 1 or k DC. This is the DC gain that we can use. Okay. So I think like for pendulum case, we designed our, we obtained our gains using comparing two transfer functions, right? The objective here is like we want to take into real-time inputs requirements. So for example, your aircraft is a physical system and it cannot, like you say, give me a roll of 100 degree or a force of 200 newtons or newtons. It has physical limits. So your inputs are limited by the design or capability of the physical system, right? So what in this chapter, what we want to do is we want to incorporate that in obtaining our PD gains or the controller gains. Okay, so let me explain you that. So this is our actual open loop system. That's anything. It can be your roll angle to aileron, your theta to elevator, whatever. So it's a second order open loop transfer function. And your U, because your PD control, right? It does not. It gives you whatever the error multiplied by Kp. That quantity can be any quantity, right? If you're really far away from the desired value, then it will be a huge value, which your system is not capable. So you are putting a saturation block here. So basically what we are saying is your U is limited by U max and U min, right? That the system cannot apply more than that particular input. Okay, so you put a saturation block saying whatever is the output, actual output of the controller, you pass it through this saturation block. That means it will, if your output is greater than this value here, it will curb it. It will make it constant. Okay, so so this is U max here and this is the U min here. So you can apply a saturation block such that we can keep up the input coming from your PID constrained actually. Okay, and then you apply this PD control. So whatever Y we have a commanded Y. So your error multiplied by Kp. So error, what is error? Error is Y commanded minus Y. So the error between what is commanded, what is desired, minus the actual output. So this is the general approach we will apply. We will not use Ki unless we find a steady state error in that. Okay. And it is also not desirable to put, even if there is a steady state error in the inner loop, it's okay. So for example, it's all right if I command 45 degrees of roll angle and I only get 40 degrees, but always 2 degrees less, because the objective is the heading change. So we will apply the integral control on the outer loop because that is more important. Go to 30 degrees north. That has to be exact. You cannot do a compromise there. But the roll angle plus minus 2 degree, 3 degree, we can handle that steady state error and take care in the outer loop, because inner loop integral control can make things unstable because it changes the order of the system, and so it's not desirable to put integral controls in the inner loop where you're actually dealing with the system, right? Roll to aileron is like actually dealing with the physical system, whereas in heading change to roll is not actually dealing with the system first. Okay, so it's not desirable to use integral controls in the innermost loops because so you should be able to handle steady state errors where you can take care of those steady states error in the outer loop. Okay. So the basic concept here is how do we choose Kp such that we never get saturated. Saturation is not a good desirable quantity. If you're always like, for example, your input is always saturated or most of the time saturated, it's not a good quantity. I'm always applying the maximum input and I'm not able to get there. So you want to design your control such that it only saturates when at the boundaries of your system, when you're demanding the most out of your system. Let's say I want to go from 0 to 45 degree. That's where your U should be maximum. If you're not doing that, then your U should be below your maximum. And how do you choose your gains for that? So if you see, our U is equals to Kp into E plus Kd into E dot, right? That's the basic input, right? So your input is proportional to the error and proportional to the error dot. So at time t equals to 0, there is no error, right? When I'm here, I am commanding 35 degrees, then at that time there is no roll rate. So that means your E dot is 0. So you can cancel that part. You're remaining with this part now. So you can say, what should be my Kp? Your Kp such that when I have Emax means I'm trying to go from 0 degree to the maximum roll allowed, 45 degrees. Then your Emax, and that's where your U should be maximum. So that's how you choose your Kp, because most of your input comes from Kp. So if your Kp is designed such that at maximum error or in the maximum tracking error, your input is maximum. So that's how I can select my Kp. Kp is Umax over Emax. So that means you will only get maximum input out of your system when your error is maximum. Otherwise, you will always stay below the limit. So you will not saturate your input. Saturation is a nonlinear quality. It's a discontinuous function. It can bring a lot of other undesired behavior to your system. So the idea is to keep your U below saturation limits. And the way we do it, choose our Kp in that way. Okay? Questions here, how do we choose Kp here? It's basically maximum error gives you maximum input. That's your Kp. Okay, so we got our first gain in. And then you find your, so this is our closed loop transfer function. So this transfer function is U to Y, and this closed loop transfer function is from Y to Yc, right? So that's the exercise we have done. So it's a closed loop transfer function, and which is a function of Kd and Kp, right? And this is your desired transfer function, right? Desired means you can choose your zeta, you can choose your omega n, that's your user quantities, and then you can compare coefficients, right? When you compare coefficients, your omega n is A0 plus B0 Kp. So you see that your omega n, we could have done a way where we could have chosen omega n first and then chosen Kp. Here we found Kp first, and then we can see what is the omega n. And then we can compute Kd by comparing these two coefficients here, 2 zeta omega ns with this, and then you get your Kd. So that's the standard approach we'll be taking here. Okay? Questions? No, right? So, and zeta is the quantity of interest here, because omega n comes from here and zeta is the defined 0.07 or 0.7 or 0.8, whatever you get desired behavior you need. So that's the damping ratio you have. Okay, so this is the standard approach that we will apply throughout the design of this. And I think everybody's mass spring damper system going at 1. It should not, because there is a DC gain is there, so it goes, it does not go exactly equal to 1. You have to either multiply your input with that DC gain. Otherwise, mine was kind of reaching at 0.6 or something. Okay, so let's design the first directional autopilot. Okay. So this is the overall gain. So first quantity of interest is this here. So that's your transfer function from aileron to phi, which is the roll angle. So we are interested in first controlling the roll angle, and so the overall transfer function was this multiplied by this, but if you separate them out, you can get P out of it, because we need phi dot to multiply to Kd, right? So you solve in steps. First, just deal with this transfer function here, this quantity here. Once we deal with this, we go in the second step to compute what is the desired phi to give you a desired turn rate, that is course angle, desired course angle. Okay, so that's how we will focus on the first part first, and then we will move on to the second part. So so the objective is to get a desired or commanded roll angle. So I say go to 30 degrees, so it should maintain 30 degrees from there on. So the idea is again same, we are using a KP KD controller here, so PD controller, and this is the transfer function that we got from there. A phi 2 and A phi 1 are the quantities, are the coefficients, and when we apply that, we get this closed loop transfer function here. Okay, so this is the ratio of phi commanded over phi, or transfer function of phi commanded over phi. Okay, so let's see what is the DC gain here. Putting S equals to 0, what do we get? If I put S equals to 0 in this equation, what do I get? 1. That means at steady state, phi equals to phi commanded. That's good, right? That's what we want, right? I want my phi to be phi commanded. So that's the idea. So we choose your KP according, again, so that it does not saturate. It's your delta A max. Delta A max is the maximum deflection your aileron can have, and your E phi max is, I generally go from 0 to 45 or 0 to 30. You can choose it to be minus 45 to 45. That can be 90 degrees. So you can, but that can be, your KP will be really small. So it will be slow then. But if you say you always go from so if you have to go from minus 45 to 45, you go from 45 to 0 and then 0 to 45. That you can consider that, and then your E max can be 45. Right? The error max can be 45. Again, all the computations has to be in radians. Degrees, when we talk, it's okay, but MATLAB understands radians, so that's it will be radians there. Otherwise, there will be error. So we just compare coefficients, right? So we have computed KP from here, and then we compare coefficients. And omega n phi can be from here. Omega n phi square equals to Kp phi A phi 2, and Kp comes from here. A phi 2 is already known, so you get omega n from here, and then you can plug that in. This is not like rocket science. We are just comparing coefficients here of two same second order equations. We want to make them same. So what should be the gains such that these two equations are same? Their coefficients are same. That's all we are doing here. So that gives us at least our first cut. And you will realize that when you put to the actual system, you might or you will need tuning these parameters. So that's the first part. So I would suggest, like when you are tuning your gains, you remember I told you you can get a transfer function in MATLAB using, you give the numerator coefficients and denominator coefficients, and it gives you a transfer functions, and then you can see its response by saying step sys. Okay, so if you give a step command, it will tell you exactly, it will give you a response of if your phi equals to 1, then what will, so you will see if there is steady state errors, how fast it is converging and all that stuff. So you can then tune your gains. So when you're tuning your gains, I say don't apply actually to the system first. First tune here. Get a desired response first. That this is the response I'm looking. Smaller overshoot, less oscillations, and then you tune your gains. And once you fix your KP and KD, then we can go ahead and put in the actual system. But for tuning, you don't have to go first to the real system. Just use the step sys command and MATLAB to tune the gains. Questions here? Here. So this is Kp, and your omega n phi comes from So square root of kp phi a phi 2 is your omega n phi. So that is the natural frequency of your inner loop system. And now this was the inner loop. See, it was assumed that because inner loop is much faster, we are saying that the DC gain from phi c to phi is 1. Okay. And so again, this says that the current suggestion is to not have an integrator in inner loops, including the roll loop. So, innermost loops, we should avoid integrators. Using the kind of that's. So now let's come to the coarse loop now. Coarse loop is the outer loop, okay? Because if you remember, to change coarse, I need, so your phi is what goes in. So to control the yaw of the aircraft, you need to roll. So what should be the roll such that I get a desired yaw angle? So right now, the coarse is 0, for example, and you want to go to chi c equals to 45 degree north or something. So what should be your roll angle? How much you should roll? You roll until you get your 45 degree of, so that's the objective here. So the way you design this is, if you remember what was the DC gain for the previous loop? 1, right? So that means here we can assume the DC gain equals to be 1. That means as soon as you say phi commanded, you get it. That's the, so that inner loop that then becomes 1 here, and then you go ahead and again design. In this case, we will see that we need a PI controller rather than a PD controller. We need a PI controller because there is a steady state error. If you just use a PD controller, there will be steady state error. So that's why we use a PI controller instead of PD controller. Okay. So now so this is the closed loop transfer function. Once you compute the closed loop transfer function, what is closed loop transfer function? Chi c over chi and d and this dx over chi over dx, right? So you will see, so we have two transfer functions, right? One for the disturbance to the chi and one is from chi command. So if you put s equals to 0 here, what we get? If you put s equals to 0, you get 1. That's good, right? So chi commanded equals to chi at steady state. And what about here? What? 0. What does that mean? That means the disturbance, whatever those terms that we neglected and lumped them together at steady state, there will be no effect on the coarse angle. That's good, right? So that's like we are guaranteeing that whatever assumptions we made or things we did not consider, that disturbance will not affect our coarse angle. We can guarantee that coarse angle will go to coarse commanded, whatever the disturbance term is. So that's the awesome part here we have. Okay. So questions here? So again, like I'm saying this, this is a closed loop transfer function, but it's like taking the Laplace and then finding the different ratio. Rather than u to chi, we are finding chi to chi commanded. Okay, so that's the interesting part here. Questions? So now what will this give me? This basically gives me phi commanded, and then phi commanded is immediately from the lower loop because it is faster. I go and so now next thing is how do we choose the gains here, right? Okay, we chose whatever kpx and kix is. You eventually you get chi commanded and disturbance is rejected. The frequency of your outer loop, inner loop. This is where the DC gain. So you are immediately getting a commanded roll angle from phi to phi commanded. Yeah, like phi becomes phi commanded immediately from looking from the speed of the coarse loop. So for coarse loop, input is commanded coarse and output is coarse, and the transfer functions. There are two transfer functions here. One is from commanded course angle to course, which is this. So if you see, the final value theorem is basically, if you keep s equals to 0 here and this everything away, so it becomes 1, and when you go s equals to 0, because there is a 0 here, this whole thing goes to 0. So that means disturbance is rejected. So disturbance is rejected here, and at steady state chi equals to chi c, basically. So that's the whole idea. Okay, so how do you choose gains now? So this is the closed loop transfer function. To choose gains, basically we need to compare the denominator with desired transfer function, second order transfer function. So the idea here is, obviously here, let's system here. So that's first you choose the inner loop's frequency, natural frequency, because that is the speed of the system. So you want inner loop, the outer loop to be slower than the inner loop. Okay, so let's say this is omega n phi computed in the previous loop for the roll loop, right? That's what we computed, which is some ratio. This omega s is the separation between the inner loop and the outer loop, and we are suggesting it can be between 10 to 15 times. So depending on your system, you can choose it to be 10 times or 15 times lower than the inner loop. So that's how you get your omega n chi, and basically we are just comparing the coefficients with the second order transfer function again, and you get your omega n x here, and if you compare coefficients, we can compute kix from here, and from here we can compute your kp x. So we get both kp and ki gains for the outer loop. Okay, so so if I have to implement this, so implementing will be phi commanded will be equals to kp phi no, that's the aileron, sorry. Delta A equals to kp phi commanded minus phi minus kd phi into p. P is the roll rate. We don't have a phi dot directly available, but p is available to you. And at smaller angles, p dot or phi dot equals to p. So you can take that directly from your state. This is coming from your s function, right? So s function, you have p available to you. So that's one. So that's your delta A, and you can compute your phi commanded equals to kp chi, which is kp chi, that is chi commanded minus chi plus ki. I think this is an integral. So ki into, what is that error? Chi c minus chi from 0 to t. So we'll see how do you actually implement this, but this is phi commanded, so you compute phi commanded and this put into this loop here. So those two controls. So first you compute phi commanded, and that you send it to the roll loop. So one is called course loop, one will call roll loop. So you will call course loop function, it gives you a phi commanded. This is the commanded roll angle. I want my aircraft to go to a particular desired heading, and then your aileron, your second loop gives you the aileron command to give you that desired roll command there. Okay, questions? Yeah, looks kind of, when you use these symbols k chi ix kp phi, looks like horrible, but it's not horrible. It's just comparing coefficients and getting values and just putting them in. More horrible thing will be tuning. You will say, hey, Raj, we got our gains, but they are not working as when we put in. That will be the challenge there, because now you're applying this separate. We have done so many simplifications for each thing, and then we are computing them. Then all of them you're applying to that 12-state motion model. That's where the problems will start coming in. And But I will admit this will be the most challenging assignment you have done so far. So be careful from starting itself that you are computing your gains properly. So maybe because time is not there, remaining part of this I will record all the different loops. I will record it, post it, so that that will be available. But just let me give you a glimpse. Okay, folks. So this is where we left in the previous class on Friday. So as I said, this is the course loop, and the course loop, the input is commanded course angle, right? And we are using a PI controller here, so PI controller, right? And the inner loop, which was in the previous slide, the idea here. So if you see, first is like, so basically we are comparing this with s squared 2 zeta omega ns plus omega n square. So this is a desired transfer function, right? So we are comparing coefficients. So this is equals to 2 zeta omega n, and this is equals to omega n square. So that you compare these and you can compute the value of kpx and kix. Okay, so so that's basically, when you compare, you can write these equations, right? So from here, so now idea is, how do you choose omega nx, right? Because if you choose omega nx, which is the natural frequency of the course loop, so the idea to choose this, because if you choose, so zeta is, we can choose to be 0.7, and then if we choose omega nx like a ratio, like, so this is the natural frequency of the roll loop, which was the inner loop, and we can choose the course loop to be omega x times slower than the omega n phi. So you will know this expression, and now you can compute kpx from here, right? So kpx is given as 2 zeta x omega nx. Zeta x is the design parameter, which is, you can choose to be 0.7, and omega x comes from omega x is the basically how slow, or the ratio of your frequency of the roll loop versus course loop. Okay, so bandwidth separation, that's what we call it. So basically you can choose it to be around 10. So if you see, it will be omega nx will be omega n phi divided by 10, so 10 times slower than so you can get kpx from here and kix from here, because Vg is already known, gravity is already known, so all the parameters are known except zeta and omega n. Zeta x can be chosen as 0.7, which is the damping ratio. Omega n for course can be so omega n phi divided by omega chi, which is the bandwidth separation. Okay, so that's how. So again, this one here is the DC gain for the inner loop. The whole inner loop is represented by 1. So at the speed of the course loop, the roll loop is immediate. Like you get phi commanded to phi is just 1. Immediately you get your commanded course angle. Okay, so that's the idea here. So if what we have learned here is basically two things. So this is lateral autopilot, right? Lateral autopilot. You're controlling. I think there is one more side slip, but in lateral autopilot, we are controlling your. So the first loop is roll loop, which is the roll loop is delta aileron to phi, right? And so this can be assumed that, like, for that we are saying that once we use the PD control here, a PD control here, phi commanded to phi. So this can be assumed 1. So you compute your delta A such that phi goes to phi commanded. Okay. So delta A will be Kp phi commanded minus phi minus Kd Kp phi Kd phi. So that's your aileron input computed using into P. This P basically is equals to phi dot, and you're getting, this is coming from S function. So that's your roll rate, and this is also coming from S function. Right, so you can compute delta A from there. So that's the inner loop, and the outer loop is basically your phi commanded. So what phi commanded should be, so phi commanded will be equals to Ki Kp chi into chi commanded minus chi, that's plus 0 to t Ki chi chi commanded minus chi dt. So basically that's the phi commanded. So you compute phi commanded to get a desired coarse angle. That then goes to the second loop, the inner loop, which provides you an aileron input to give you that commanded roll angle. Okay. How things will look. So again, similarly, if you want to, so we are using here, so the transfer function between rudder, the side slip angle, beta to rudder input. So rudder is at the tail, right? So that vertical tail is your rudder. So that's your rudder, and so this is a first order transfer function. We are using a PI controller here because again we cannot afford steady state here, steady state errors. So basically that's the objective. This is the saturation block which keeps your rudder input to rudder delta R max to delta R min. And again the objective is to keep beta commanded, in this case beta, to be 0. So rudder will actively work to keep beta to 0. Okay, so similar approach, the closed loop transfer function from beta to beta commanded will be this. Again, all we have to do is compare the coefficients of this. So I can write those coefficients, s square plus 2 zeta omega n s plus omega n square. So we just compare coefficients of this equation and this equation. So in this case, your Kp is chosen such that the saturation doesn't occur, so delta R max or error max. Again, this is the maximum input, allowable input, and this is the maximum error you can think, this error here. So let's say in the worst conditions your beta angle will be 30 degrees, so you have to go from 30 degree to 0 degree, right? So that's EB max. From that you can compute your proportional gain Kp beta, and once you have Kp beta you can compare. So you can compare this and this, so which is equal to A. So A beta 1 plus A beta 2 Kp beta equals to 2 zeta omega n. So zeta can be chosen as 0.7, or it's a design parameter, 0.7 or something like that, and omega. So that's all you need here. And Kp is already known, so you know Kp, you know this from transfer functions, and you know this, so you can compute your omega n beta, and then you can compare this with this omega n square, you can get your Ki beta. And you can see if you put the final value here, the DC gain, putting s equals to 0 in this transfer function makes, and that is equal to 1. So this will be equal to 1 at s equals to 0. So that means your beta goes to beta commanded. So that's the idea here. Okay. Like later on. So this is the summary of the lateral autopilot. This is so inner loop. We have basically three. You have to write 3 PID or basically PID controllers to right. This is the first one. First PID controller is called roll loop. Okay, the roll loop. So the roll loop, the idea, the output is delta A. So you the basic idea is you should know your EFI max, delta A max to compute. So basically these are the two parameters you will need to compute KP phi and KD phi. It has to be faster loop. The other loop is the outer loop, which is the course hold. So the output, so input is phi commanded and output is course. So phi commanded is computed here, and then it goes and uses the roll loop to compute delta A. Okay. So the idea here is the design parameter. You have to keep it slower. The outer loop has to be slower. So when you choose omega n, chi has to be equals to omega n phi divided by omega x, or 10 times slower, and you can choose your damping ratio. So that will provide you your kp chi and ki chi. So we are using a PI controller here, and for rudder also we are using a PI controller. These are the design. So in blue these are the design parameters. So you can choose as a user that will then be used to compute your gains. So you will have KP beta. So basically KP beta and KI beta is what these two parameters can be used. Okay, so that's the idea here. Again, the lateral autopilot only has 3 controllers. So 3 loops, or you can say that. So the roll loop output will be delta A, and the course loop, the output will be phi commanded. So the phi commanded then goes to the roll loop, and then you compute delta A. And for this, the Sideslip input is beta commanded, and output is delta R. Okay. So that's the idea. That's the summary of the lateral autopilot. We'll when we see the MATLAB code, we'll see how it works. But that's the summary of it. What you do is that's how you choose your gains in the first place, and then okay. So this basically slide tells you how to tune it, because once as I said, because we have made so many simplifications, right? We have made simplifications. So here next step is to tune them, because we have made simplifications. All these 6 gains that you will need, are computed from the previous slide. Are you might need tuning when you put them to the actual your simulator, right? Actual simulator, that is your 12 state S function that you already have. the idea is, let's say you first put them and then see things are not working the way they should, then you, for example, you want to tune this, right? So you increase your KD fee first, let's say until you go to instability, like, and then back off by 20%. Okay, so that makes it, and then tune KP to get acceptable uh, step response. So first start with KD, make KD as big as possible, keep increasing it until system becomes unstable. So you have to find that boundary of instability and then come back by 20%. Okay, so we have to choose KD such that it is at 80% of instability, and then you choose your KP, tune your KP. So again, when you're tuning means you increase it, if performance becomes good, you keep increasing it, otherwise you keep decreasing until performance is acceptable. Similarly here, use KPX to get acceptable step response, and KI, as I said, the role of the integral controller is to remove the steady state error. So you keep increasing KI until you get rid of steady state error. So get that boundary, not more than needed, but just where your steady state error is minimum. Similarly, in this, you tune KP beta. Again, tuning is you go in one direction. If the performance is improving, you keep going in that direction, and you stop where performance starts deteriorating. That's the idea. And then KI beta's role is just to remove the steady state. So keep increasing KI beta until you reach a point where there is no steady state error. So that's how you tune your lateral autopilot gains. Okay. So once you have written these PID loops, right? So this is called the state machine kind of thing. So if your altitude is below takeoff, so that you're segmenting your airspace into 3 segments. One is below takeoff, H takeoff, right? So if your initial height is below takeoff, then you are in takeoff zone. So in takeoff zone, you give full throttle. You don't delta T equals to 1, and you use theta. What should be your commanded theta? All right, you regulate. So how do you compute theta C, control theta C? Using your elevator. So you're just using elevator with full throttle in the takeoff zone. So that's how you determine what should be the inputs to my roll loops, right? Or to your peer. In the climb zone, again, full throttle, delta T equals to 1. And now you're regulating your airspeed, VA, using either pitching down or pitching up. So because how would you otherwise change your airspeed if your delta T is already 1? Airspeed can be changed by throttle, right? If that is full, maximum, but you still want to increase or decrease your airspeed, then you can use pitch angle. So you can compute your desired theta for desired airspeed, and then you can again call that pitch loop to compute your elevator commands. And then third is altitude hold zone. So you're close to the altitude. That's where if you're below, so your HC, regulate airspeed by commanding throttle, because if you're below, then you can increase your airspeed and go up. Okay, and then if you're up, then you can control your airspeed using pitch. And descent zone, like if you're climbing down, give a 0 throttle and then regulate airspeed by commanding pitch angle. So we'll see how we will implement it in the next video or next class we will have after the spring break on WebEx. But yeah. So I will post the assignment today. At least you guys can start writing these PID loops that we will then call in the state machine to control. Again, you guys are designing an autopilot, so it will be really complicated, but we will be helping you. Okay. Have a great weekend. Be safe, be healthy, maintain social distancing. And yeah, so any questions regarding WebEx or anything, just email me. Okay. So before we move, so longitudinal control autopilot. So we have already covered the lateral autopilot. Now we are moving to longitudinal autopilot, and longitudinal autopilot is kind of a little bit more involved than the lateral. So lateral only had your phi and chi and beta, and was kind of simple that to. But here things are, the main is the altitude here. Okay, so this chart basically shows you the three different zones. So there is a takeoff zone. So you in your simulation you have to put that below a altitude your aircraft is in takeoff zone, and then you are in a climb zone until you reach this. So HC is the commanded height. That's where you want to fly your aircraft, and you add a plus minus buffer zone basically. So this is minus H hold and this is plus H hold. So between H takeoff to H minus H hold is your climb zone. So basically in takeoff zone your delta T equals to 1, right? So that's the full throttle, and you have to control whatever desired theta C is, and that theta C can be controlled using delta aileron. So you will have a roll loop, a pitch loop, which will the output will be delta aileron and the input will be theta C and theta. We'll see how it will work. So that's how you will call a PID loop, this pitch loop, to keep theta to theta C. So basically you have to take off with maximum throttle and a constant pitch angle. In climb zone also your delta T equals to 1, and we will discuss all these loops. So basically here we have one loop, pitch loop. Here you have to control your airspeed in climb zone. So the airspeed can be, let's say, 35 meter per second or whatever VA commanded is. So you have to control using pitch. So there is a loop called pitch, airspeed from pitch. Okay, so this is how it will work. So the output of this airspeed to pitch loop will be a theta commanded, and then you will you can again call this loop, pitch loop, to give you this desired theta commanded. Okay, so that's how it will be. And similarly in altitude hold zone, depending on if you are below the altitude hold zone or above the altitude hold zone, you have to so here you want to, if you're below, you control your airspeed using throttle. So you use delta T to change VA, and in this case you will use pitch to change control your airspeed, altitude. See, and there's a reason. For example, if you are below, right? So if you are below, you want to go up, so you can increase lift, right? So if you increase lift by increasing VA, so then you go up. And when you're here, basic idea is you keep your VA constant, and you go up and down. You can go down by just choosing a negative theta. All right. So, and then in descent zone, just cut the throttle and just regulate your airspeed by pitch. So basically, if you want to go down, you just theta can be negative here too. So pitch down and just fly towards the ground. And we'll see how so this will be basically kind of a state machine. So again, longitudinal autopilot will be more complicated. We will have to so basically these will be your flags, and you will call these different loops When we see the MATLAB code, this will be more clear how do you actually call these different PID loops. Okay, so our first PID loop for the longitudinal is the roll loop, or sorry, the pitch attitude hold. So the idea is to compute your elevator, right? Aileron was, I keep saying aileron, but aileron was to control roll. So we are trying to choose a the elevator angle to give you a particular desired pitch angle, commanded pitch angle, right? So this is the closed loop transfer function we have, and so in the closed loop, so Q can be considered as theta dot. So that's theta dot, you multiply by KD, and then your error goes in. You have closed loop transfer function. Here. The only problem here is if you find that DC gain, right? DC gain is like S equals to 0. When S equals to 0, this is your DC gain, which is not equal to 1. Okay, so that's very important. Your K theta. Okay, so when S equals to 0 means your K theta DC is this, right? Because this term and this term will appear in K theta DC. Again, so to choose Kp theta, we have again same approach so that this doesn't settle. The only thing is this is different here. So basically idea is you sign, this is to avoid that, because there is a negative 0, because the sign of A3 theta is negative, and because of that we need Kp theta should be of different sign, of the opposite sign, because of A3 theta. So if it is negative, then Kp will be negative. If it is positive, Kp will be positive. So depending on your okay, so you compute your Kp theta from here, and then you can just compare coefficients of this and this. So from here we can compute omega and theta, right? So omega and theta is this, because you have computed Kp theta from here, and then you can compare this and this here to give you zeta. Oh, sorry, not zeta, but Kd. And zeta is your design parameter. You can choose it to be 0.7 or 7 or something. So that way you get your Kd and your Kp. And so this is in a loop. We are not using any integral control here, but so the idea is, because it's a non-unity K theta DC, that means your theta will not go to theta commanded, but it will go theta commanded into K theta DC. So this is what your theta you will get. So not immediately. You will have to take care, you have to put this in the outer loop design. Okay, so that's the pitch loop. Again, nothing fancy here. We are just choosing our Kp first so that it doesn't saturate. And then based on Kp, you're comparing these coefficients of these two equations and computing omega and theta and Kd phi. So now let's go one more step. So now this is altitude hold using pitch. So basically, how do you control your height using theta? And let's see, right? If theta is positive, your height increases. If theta is negative, height decreases. So that's it. Basically, height can be controlled using theta. Okay. So this is the outer loop. The height is the outer loop. So basically, this loop, the output will be theta commanded, and theta commanded will then go to your pitch loop, which you will get the delta E. So your Okay, so height commanded, basically you get theta commanded and then theta commanded. So this is the outer loop, this is the inner loop. Inner loop will be faster, but remember the inner loop has a DC gain of k theta dc. So this is the inner loop basically. If you see, this is the inner loop here. Okay, so this theta, because this theta is going to this, whole thing can be replaced by k theta dc. This whole thing. Okay, this whole thing basically can be replaced by k theta dc for the outer loop construction. Basically, in outer loop we are using a PI controller. So the next basically gives you a simpler. So the whole inner loop, the theta loop, theta commanded to theta is replaced by k theta dc. That at the speed, the outer loop speed frequency, theta commanded is the output is just theta commanded into k theta dc. Okay, and the objective is now to get a commanded height. So now we are using a PI loop. There are two inputs, one is height commanded and disturbance. And when we are using a PI, when we compute the closed loop transfer function, we get these two. This is the closed loop transfer function. So to see what is the disturbance gain, because there is, if we put s equals to 0, you will see there is a s here, so this whole thing goes 0. And let's see what happens here. This goes to 0. So basically this goes to 1. Yeah, so this is equal to 1 and this is equal to 0. So that's what we wanted, right? We want h commanded, height goes to height commanded, and the disturbance, this is rejected. So that's the objective. Perfect. So the PI control on altitude ensures that h tracks height commanded with 0 steady state error and rejects low frequency disturbances. That's perfect. So now next step is how do we choose, so this is coming from previous block. Now we have to choose kph and kih. That's the next. So basically compare the coefficients of desired characteristic equation to this, and then you will get the coefficient and the gains. Again, this we want, because it is outer loop, we first select the natural frequency of the height loop, which is like can be 10 times lower than the theta loop. So this was computed in the previous block. It comes from the pitch loop, and this is like you can choose it to be 10, so 10 times lower than, so your height loop is 10 times lower, so it will take 10 times. So if it takes 0.1 second to go from theta to theta commanded, the outer loop height will take 0.01 multiply, like, so total 1 second to go from height to height commanded. So the outer loop is slower. You can choose this to be 0.707. So once you have this, you can compute kph. So you select this first. Once you have this, then you can select this is known to you, this is known to you, and this is coming from here. You can find kih, and once you find this is 0.707, this is coming from here, everything else is known, you can compute kph, kih. So that's how you get these two gains in this loop. Okay, so that's your height, controlling your height using theta. And then, so that's the outer loop, and then controlling using delta. So delta elevator controls theta and theta controls height. Okay, so that's the two loops together here. Okay, so next is, so theta can be used to control height. Theta can also be used to control your airspeed. So airspeed can also be controlled using throttle, but so airspeed can be controlled using theta and delta t. So right now we'll see how it can be controlled. So if you are at a above altitude, if you want to decrease airspeed, you pitch up. If you want to decrease airspeed, you pitch down, right? So VA increases when theta decreases, and VA decreases if theta increases, right? So pitch, when you pitch down, your VA increases. When you pitch up, your VA decreases. So that's the logic here. And mathematically put, we have a transfer function here, a first order transfer function that we computed in previous lecture. And so the idea is to compute theta. So if you remember, the inner loop can be assumed, because this is the outer loop, it is slower, can be assumed at this speed. Theta commanded to theta is just assume that whole loop can be replaced by this DC gain, and we are again using a, see, the outer loops are always a PI. You will need a PI controller instead of making a PD. The standard approach is used to PI controller, and because when we use PI controller, we make the disturbance go to 0, and the VA commanded to VA transfer function equals to 1 at S equals to 0. So when you put S equals to 0 in the closed loop transfer function, this goes equal to 1 and this goes equal to 0. That's the idea. That's why, and that is because we are using a PI controller. Okay, so this is the closed loop transfer function, a ratio of VA command. Again, you see there is a bar here. That means it is the deviation from the trim condition. So VA commanded is equals to the trim condition, moving away from the trim condition. So that is your VA minus V trim we talked about. Okay, again, so everything is so the ratio, the closed loop transfer function is this. So at S equals to 0, DC gain is 0 for this. So that means the disturbance is rejected at low frequency, and the VA commanded to VA equals to 1 at S equals to 0. Okay, so that means good. We can go to a commanded airspeed by changing theta and reject the disturbance. Yeah. Okay, then gains, we can just compare the coefficients with the desired characteristic. The assumption here, because we have used the inner loop is replaced by k theta DC, and this can only be done when the outer loop is slower. There is a bandwidth separation there. This is to compute the equation, and that comes from here. Again, the first step is to first choose a natural frequency which is slower than the theta loop, because see, so when to do that, we choose omega n v2 to be 10 times, or 10 to 15 times smaller than omega n theta. And once we have this, we can compute the ki v2 and kp v2, just comparing coefficients of this and this equation. We're just comparing here. So s square with s square, this with this, and this with this. So that's what we are doing here. We are comparing coefficients here, and okay, so again, first step is to choose the natural frequency which is slower than the inner loop, which is the theta loop, and the airspeed natural frequency. And again, we are doing the airspeed from pitch, so that means we are controlling airspeed VA using theta, and then theta, to get theta we'll use the inner loop delta E. So there is one loop here. So the same loop is used everywhere. There will be one loop and then one PID loop here. We'll see how we will implement it later in class, but basically we're just comparing the coefficients. So you can choose omega n from here, and zeta is again 0.7 we can choose, and then that will give you AV1, and these coefficients k theta g, they are all coming from our transfer function computed there. Okay, so airspeed from pitch, and then again, as I said, airspeed can also be increased using throttle. Like for example, when you're taking off, airspeed is 0, so that's where you want to use maximum, or you can. So the transfer function here is first order transfer function. Again, remember we are using bars here. That means these are the deviation from trim conditions. So your aircraft is already flying at VA star or something. The idea is to move away from this. So VA bar is the deviation. VA bar equals to V trim minus VA. Sorry, VA minus V trim. Okay, so that's VA bar. So we are talking about the deviation here. This transformation, if you remember, we got after linearization around the trim point. Again, the idea is to take VA bar to VA commanded bar. Okay. So we are using a PI controller. Again, why PI controller? Because we know that on this PI, when we compute the closed loop transfer function and the transfer function ratio from VA commanded, again there should be bars here. I think that's here. So that's equal to 1 at s equals to 0. When you put s equals to 0, you'll see that DC gain is 1 here and DC gain is 0 here, because there is a s in the numerator. That is achievable only with PI configuration. Okay, so that's the closed loop transfer function. Again, delta t is delta t bar is delta t minus delta t. So this is the deviation, the what extra throttle you should apply. That is what is being computed here in this loop. Okay, so that means when you the actual throttle will be delta t bar plus delta t bar plus delta t star. So this will be extra to the trim condition. That is the object. So to get a deviation in airspeed from trim condition, you need a deviation in throttle from trim condition. That's the idea here. Okay, so then again, how do we compute Kp, Ki and Kp? By coefficients. Again, we compare it with this desired equation, and so now you have to choose omega and V here, because this is again the inner loop. There is no outer loop here. This can be so we will choose omega and V, and delta V can be 0.707 and omega and V, depending on how fast you want this. Like, so you can choose. So these are two design or tuning parameters that you have. So you in simulation, you will have to choose what should be omega and V. That gives me a good response here. That's the idea. So that's the idea, that once you have these two, you're just comparing coefficients of this with this and this with this. So we can get KIV and KPV when we compare the coefficients. So these are the two gains you will need. Again, here what we are doing, we are saying delta T bar equals to KP into VA bar commanded minus VA bar minus plus KI 0 to T. The same error, this is VA bar commanded minus VA bar
into dt. So that's your delta t bar. So that's how you implement. We'll show you how exactly we implement a PID loop, but that's what this means. We are using computing KP and KI using these two here. Okay, so yeah, we are kind of done with all the loops. So let's see how these look. The longitudinal autopilot look like. So we start here when you are below. So basically, you're always checking on your height, what your height is. So when you check your height, you can determine which of these categories your aircraft is, and based on that you can choose what control to call. For example, if you so there is always a loop which is checking h for h continuously, so that you can switch between different cases. So this is case 1, case 2, case 3, case 4. There are 4 cases. So basically, if your h is less than h takeoff, then you are in takeoff zone. There you fix delta t. So remember the objective. So the objective of the autopilot is to compute delta t, delta e, delta r, and delta a. Right? These 4 inputs are needs to be computed. So in the first, so because this, so delta a comes from your roll and course loop. So that's different. So this delta a we can remove. So basically these 3, and delta r is for the side slip angle beta. So only these 2 needs to be computed here in this. So we need the longitudinal autopilot basically computes delta t and delta e, throttle and elevator, right? And delta r and delta a comes from your lateral, which is controlling the course angle and roll angle and side slip angle. So when you are in this zone, takeoff zone, your delta t you choose the output equals to 1. That means full throttle, and then you want to you want to take off at a desired pitch angle, right? So then this is where you call the course loop PID, course loop PID controller, where this goes in, the output is delta E. So that's how you compute. So every place you can see you can compute two control commands. So delta T is already fixed, and then from here you can compute delta E using the course loop. Okay, so the 2 are done for now. Next, let's go to the second step. So second step again is like when you, if your height is above takeoff and below h minus h hold, hc minus hold, that means you are in climb zone. So in climb zone, again your throttle is 1 and your pitch, so you're basically controlling your airspeed using pitch. Okay, and once you compute this, so this is the output of the airspeed to pitch loop, and then you can again call your 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 pitch loop, right? So this is pitch loop. So your pitch loop, and then you can compute your delta E again. So again, so here it will be successive loop closure. You first compute theta C. From theta C you compute delta E. So you again have delta T and delta A here. Similarly here, in the altitude hold zone, when you are H is less than HC plus H hold, then basically you're controlling your VA using delta T, and your theta C, your height using theta C, and then again you will call the pitch loop that will give you delta E. Okay, so so again delta T from here and delta T where this goes. So again successive loop closure. In the, and if you are above this, if you want to land descent zone, basically you compute, if you want to land your aircraft, you cut the throttle to 0, and you control your VAC using theta, and the output is theta C, and then theta C again goes to your pitch loop, and then that gives me delta E. So see, everywhere, so some places you are getting, so delta T is direct, all the places, right? But your delta E is coming from the pitch angle required at that place, okay? So that's pitch angle is involved. So that's how this will be implemented here. Okay, I'll show you the MATLAB code which will make this more clear how exactly what is happening. Again, this is the summary of the longitudinal autopilot. Basically, we have inner loop. This is the loop which is always called, which gives you, so the input is theta c, that's what you want to control, right? And the output is the delta elevator, which you feed it directly to the forces and moments. Okay, so that's the loop which will be called again and again. And so this is the innermost loop. Okay, and then the second loop is altitude hold, that is the outer loop. And altitude hold means you use control your height commanded using theta commanded, and then again you call this to give you delta E, right? So, and so you need a separation between this and this loop. So you choose omega h to be like between 10 to 15 to give you omega n h equals to omega n theta divided by omega h. So basically you choose this number to be 10 to 15 times, and this is the damping ratio. Again, these are the design parameters, you can choose them. These are to choose your kp theta. This for kp theta, and this you will get kd from here. Again, this one more outer loop. Here we are trying to control airspeed using theta. So airspeed using theta, VA commanded using theta commanded. So once again you will call this loop, which will give me delta E. The again design parameters are your net, you choose a bandwidth separation and a damping ratio, which will give you Kp and Ki gains for this. This is one inner loop which basically controls your airspeed using delta T. So you have to choose this and choose this to get a Kp and Kd. Okay, so that's the kind of summary of what design parameters are. Then again, tuning, this is similar to what we discussed for the, this is a standard tuning approach, right? So the inner loop, you increase Kd up to a point where it becomes unstable, the boundary of instability, and then you reduce it back to 20%. So that's the Kd theta, and then you keep, so increase in one direction if the performance is improving, and keep increasing or decreasing until the performance stops to improve. So you fix your kp theta there. Similar, so these are the some tips for tuning. So the gains that you will compute using comparing coefficients will be the first cut, and then you basically tune your gains. Now if I have to make a picture here and I draw how many, it will be all, so this one, height from pitch, airspeed using theta. So we have lateral, so we have if I draw a line here, so this is the lateral autopilot. So I'm talking how many times you have to use a PID loop. So there is one PID loop here, which is the roll loop or roll PID. So you have to write a PID which will basically be delta aileron will be the output of this loop, and it will be basically Kp phi commanded minus phi minus Kd phi dot of P. So that's the one thing. So you will compute this Kp and Kd, and then the other one, so this is the inner loop. So the outer loop is the course loop. Course loop. So I'm just summarizing the lateral autopilot. So you have to write one PID. The second PID is the course loop, which is again takes out phi commanded. The output is phi commanded, and it is a PI controller. So it is KP chi commanded minus chi plus integral 0 to t ki chi commanded minus chi into dt. Right, so so this is the course loop, slower than the previous loop. So phi commanded, then so first you call this, which gives you phi commanded, and then to get a desired phi commanded, you put in here to get a delta aileron. Okay, and third is so this is third PID. So you will have three PIDs for beta loop or side slip loop. Basically, the idea is to get a rudder input using KP. I don't remember what was a PI or PD, but let's say if it is a PI, KP will be beta commanded minus beta plus KI. I'm keeping these names same, so that for pure parameter it should be KP beta and all that stuff. So KI beta commanded minus beta dt. So there will be total three PIDs for lateral autopilot. Okay. For longitudinal, basically we have the main is the pitch loop, which is basically giving you delta elevator output, and the input is KP into theta commanded minus theta minus KD into Q, which is theta dot. So that's first loop. Second loop will be your height from pitch. So going back, height from using pitch. So the output will be theta commanded, and the KI will be KP height commanded minus height plus KI height commanded minus height dt. And then this theta commanded goes here, you compute delta E elevator. Third is again your airspeed VA using theta. Similarly, fourth is, so from here you get theta commanded, and then again you call this loop here to get delta E. The other one is airspeed using throttle, delta T. So this is directly you. So these are four. So you have four PID loops here. In total you will have to write 7 PID loops, or 7 PID functions that you can call again and again depending on which state you are. Okay, so that's these. Okay, so now this is how you see how many PID loops. So if you go back here, so here we are going over. Okay, folks, so now we are moving to how to actually implement a PID. So what we will do is write a general PID and then basically save as 6 or 7 different PID loops, and write a general code where if for example we are only using PI controller, then your KD will be 0. If we are only using a PD controller, then KI will be 0. So basically one general PID loop that you can save as 7 different files, like roll loop, course loop, pitch loop, airspeed to course, airspeed to pitch, height to pitch. So you can write all those 7 different controllers, but I'm just giving you how do you actually implement a PID in real-time system. And the need arises because we are using a onboard computer which does not have MATLAB, or it generally uses a Python or a C++ kind of language. So how do you actually implement a PID controller there? So that's the idea. So this is a general PID in a continuous time given by. So your input, which can be your delta E, delta A, delta R, delta T, or theta commanded, phi commanded, whatever, right? So that's the output of this PID controller. So it's basically your error. So error is like basically output commanded minus actual output. That's your error. And your integral is the total error accumulated over that time. So Ki into integration of the error. And yeah, the third term is your Kd proportional to the error derivative. So E dot, right? So that's the a PID sum up, like a summary of a PID controller, right? So basically, if you are using a PI, then this is non-zero, this is non-zero, but then this is zero. If you are using a PD, then this is non-zero, this